My name's Amy. I'm going to share with you a little bit where we think, as John said, the future is going for both graph and artificial intelligence. We know that artificial intelligence is very hot right now. There's a lot of progress being made. And as John showed us, graphs are exponentially growing as well. So it's probably not unusual that people would want to marry these two topics together, but they actually have a lot in common as far as their use and one influencing the other. Graphs add context for AI. And when I talk about AI, I'm talking about AI systems, so software applications that together are trying to make some kind of action or decision that's probabilistic, and that is very similar to the way humans make decisions as well. We're never really 100% sure, but we think probably it's the right thing to do. So we're going to talk a little bit about that, and then we're also going to share some of the steps that we've learned with our customers that help people move along in the process and progress. So first, an interesting example. I like this example because these things do not have anything in common for the most part. So I've got smoking and voting here. Totally different behaviors, totally different kinds of activities with different types of results. Now the interesting thing here is they actually found one thing in common, and that's making predictions. So how do you predict whether someone might be a smoker? Well, you might say age, demographics, zip code, income level. How do you predict whether someone's going to vote? Maybe the same things. But what the network scientists actually showed through various different research is that those types of demographics were actually not as predictive as their relationships. So they could tell with fairly high accuracy, get good predictions, whether somebody was a smoker or not based on their relationships. So you can imagine, and maybe that doesn't seem, once you hear it, doesn't seem so surprising, that if I know whether your friends smoke, well, I can kind of estimate whether you might smoke as well if you have a lot of friends that smoke. They also found that if you lose friends while you're trying to quit smoking that smoke, a higher chance of successful quitting. Now what's even more interesting to me is actually the voting. So this research was done in Texas where they were trying to predict whether somebody was going to vote based on their friends, and not surprising, like the smoking, you have a lot of friends that actually vote, you're more likely to vote. But what was even more surprising was they could do with even higher accuracy whether the friends of your friends voted. So if you think about that, people you don't know are more predictive for researchers of whether you're going to vote than your own first order of friends. And that has to do with the power of the networks and the, how you can make predictions based on a larger group than just individual general statistics. And these two examples are actually taken from a book called Connected from James Fowler. And over again, he showed how relationships are the strongest predictors of behavior. So not surprising why we would want to use that with AI systems, if you think about it. Now, it's not just individuals that you can use when we're talking about behaviors, but we can also use this for larger systems. So, for example, we have clients that are using it to understand contagion, financial contagion, as well as health contagions as well. But if you can imagine, the one chart on the left is looking at, yep, that's the left. On the left is looking at a contagion spread in the global markets around 2008. So looking at the pathways that things move. These are all relationships. And then the other picture actually is the trend where we see people going next is doing more local predictions. So how do I do a financial ripple effect analysis in my local market? How do I do that for a particular industry? And using graphs so you can walk those pathways and do what-if analysis. In this example, it was a shipping company that actually provided some manufacturing for trucks as well. It turns out they were very sensitive to steel prices, not surprising, maybe not directly, but the people who were manufacturing parts for them were very sensitive to steel tariffs, and then they couldn't get their parts, and then they couldn't get things done on time, and then the shippers had trouble making the commitments that they had. So trying to understand that ripple effect is another area where people are using relationships. And we're looking at economics here, but you can imagine in health and even even things like rumors, how do they spread? So thinking about relationships being strongly predictive of behavior, thinking about the ability to track how things ripple, it's not surprising that we're actually seeing graphs influence AI research. So this chart shows AI research that includes and focuses on graphs from 2010 to 2018. So you can see in the matter of 8 years, there's about a 4-fold increase. I'm kind of curious to see where we'll be at the end of this year. I suspect we'll still be shooting up there. But it's not just in research. We are also seeing our customers and people across different industries using graphs in data science. Things like fraud protection or fraud detection. You can understand why fraud might have a shape to it and patterns of behaviors again. Thinking about customer segmentation. Do I just want to look at my customers by simple demographics? Or do I want to group them by their behaviors and by the relationships they have with other people or even products? And if we're talking about products, how are the products related to each other, subcomponents, things like that, services, that might help us with recommendations. Life sciences is an interesting area as well. So one really interesting use case is to look at drug repurposing. So there's a couple organizations out there using Neo4j, one called het.io. If you're interested, let me know. I'll get you the information on them. But they actually use Neo4j to look at drugs that are already approved, look at what genes those target, and then look at what diseases are involved in those genes. And so what they're able to do is they use drugs that are already approved for one disease, and then based on the genes, look at if there are genes in common for another disease, and they can repurpose it. It gets us drugs faster for new uses and safer as well. Churn prediction we'll look at a little more in a few minutes. It's a really interesting thing to do, to look at whether, and try to estimate and predict based on relationships whether your customers are going to churn. My favorite example on that is actually in the telco industry, not just whether somebody's going to churn, but who's influential in their network that might churn. So an interesting, I find kind of a cute story, is anybody know in the telco world who's the most influential person in a subscription network? It's your mom. So if mom goes to another subscription service, another telephone company, your siblings are likely to follow. Your nieces, your aunts are more likely. So looking at what's that ripple effect of a churn, you have to know who's influential in your network. And various other industries like search, as you can imagine, very graphy. Think about Google and PageRank there. Predictive maintenance and IoT is very important. And of course, cybersecurity, anytime you're talking about a potential intrusion as well, wanting to understand those patterns. So these companies and these industries use this because they can make better predictions with the data they already have. So how many data scientists in the room? Okay, a few. One thing I hear all the time from data scientists, if I just had more information, I could get better accuracy. You already have more information. It's hidden in the data you already have. It's called relationships. Most data scientist models toss out the relationships. They're looking at things as rows and columns. Keep doing what you're doing. I'm not saying stop doing your normal pipeline, your normal workflow, but add in those relationships. You already have that data. Don't throw it out. Just add in the graph relationships so you can add in another dimension to your data and increase your predictive quality. So if we think about data science, the goals of data science are usually in 3 large categories, I would say. John mentioned the first 2. Better decisions. How do we support people and domain experts that have to make decisions? Higher accuracy, and that's all around graph-based prediction when we're talking about graph data science. And then the other goal that people want to attain is new ways of learning. AI, machine learning. It's all about learning in ways that we're not accustomed to as humans. How do you learn in a different way? And then how do I trust my results? And that is an area we're going to talk about a little bit in graph native learning. That's a little bit farther off. That's a bit where the research is heading right now, but I think it's an important step. Now there's a logical path that maps to these 3 big goals and I would say, steps to get there. And so these are very practical steps that people can get started with now. Knowledge graphs, it's a well-known, well-established way to bring in lots of information and follow the connections. Graph analytics, how do I look at my graph or my network as a whole and have insights about the entire structure? Graph feature engineering, that's about adding predictive data to my machine learning. Graph embeddings, kind of a type of feature engineering, but on more complex structures. And then the graph neural networks, which is a little bit about the new ways of learning. So we're going to walk through each one of these. I'll give you a couple examples in each area so you can kind of see how that might apply. And I should say, I'm going to go back one. I always forget to say this. The reason why I've got the arrows moving forward on this is that it's not that you go from one step to the other and then you stop using the former tools. Knowledge graphs we expect to always be around, even when you're doing very advanced AI and machine learning. Especially if you're using graphs, you're going to want a knowledge graph under there. So they're more of a layer on top of each other as you add in more capabilities. So knowledge graphs are all about being able to do connected advanced search and support your domain experts. So an example of this would be with a company called Refinitiv. They used to be part of Thomson Reuters and they spun off. They have a tool that basically layers on multiple different graphs, so not just one graph, they have multiple graphs they're bringing together of financial information. Things like corporate data that's publicly available, news that is about companies that might be in someone's portfolio or an industry, as well as cross relationships. And when I think about cross relationships, it might be something like somebody, I think John gave this example, somebody who's a board member of one area might actually be a CEO of another company, may actually have a large ownership in a third company, and perhaps they have business dealings. And so understanding those cross relationships is very important. So they put together these different graphs, and with queries, they have tools and dashboards for their financial analysts. And they basically allow the financial analysts to look at what's in their portfolio and look at credit risk, do investment risk, and they would on average have about 200 companies in their portfolio and be able to do custom weights of the relationships between things. So for example, you might decide that somebody being on the board has a lower weight for whatever reason, and somebody owning part of a stake in a company, if it's above a certain threshold, maybe that has a higher rate. So the analysts were able, I'm kind of scared of the mic, the analysts were able to basically weight things to what is important to them. And they were able to basically search and do investigations and then make their decisions. So this is supporting the experts in making the decisions they needed to do. As part of that, a little snapshot they gave us in a 1-week time frame, they were able to do about 800,000 shortest path calculations in order to rank what news to give to people. Like maybe it's higher ranking if your portfolio has a lot of oil and gas, you want the news about oil and gas to be of a higher ranking. If you've got a certain company in your portfolio, you want that news to get a higher rank. And I should kind of pause for a second and say shortest path calculations can be really intensive. So if you imagine, if I want to do a shortest path between A and Z, and there's 50 or 100 or 1,000 potential different paths to get there, I have to evaluate each one of those, all the hops, and then calculate either by hops or by weight which one is actually in your shortest path. And they were able to get 800,000 in a week, that's average what they would do, and they were able to optimize those searches to be about 10 milliseconds or less. So very snappy, very good, so that your experts could make the decisions that they needed to do quickly. All right, so the next area is graph analytics, and that's kind of a broad term. And when I talk about graph analytics, I usually mean that you're either doing queries or algorithms in order to do some kind of offline analysis. You're not necessarily trying to do real time. You're trying to understand what's the topology of my network, where are things clustered together, where are the influential nodes. I want to understand different pathways. It's usually what people mean by analytics and graph analytics. Now, just a quick aside, some people ask, well, what's the difference between a graph algorithm and a query? So you can think about a query as something that you use you kind of type in, if you're a developer or an analyst, when you know exactly what you're looking for. An example would be, how many relationships does somebody named, how many relationships does Amy have? It's a very quick analysis. How many hops out are her first her flagged friends for some reason? So I know exactly what I'm looking at. Graph algorithms, a little more unsupervised, you're running those to understand more about the whole structure of your network. You don't know exactly what you're looking for, but you want to find the best communities. You don't know who's going to be in them yet, but you want to run an algorithm to say, what are the tightest communities in my network? So when you're using graph analytics, using queries, a quick example here is in the financial sector, looking at fraud. Everybody already has a pipeline or some process for fraud, and you're really just trying to improve that. So you might want to add queries like, how many flagged account are in an applicant's network 4 hops out? That'd be an example. I'd like to know if there are any bad actors 4 hops out from somebody applying for, let's say, a credit card. You also might want to know how many common login IDs or variables of this account are common to somebody else. Maybe that's phone numbers that might be common, maybe it's address that might be common, maybe it's the IP of their login that might be common. Now, what people are usually trying to do is generate these metrics and then add them to some kind of process. So let's say somebody's applying for a credit card and you notice 4 hops out or 5 hops out. They have a high number of flagged accounts, things that are suspicious. Maybe you turn that credit card down, maybe you send them to another offer. Now, the interesting thing about this, I call these deceptively, and I'm thinking my mic's off, is that right? Yeah, okay. Away from the mic. Well, actually, I'll stay here in case it magically turns on. And it did. There we go. So I call these deceptively simple because for us, as we think about them as human, it's like, okay, I just want to go the next hop out and the next hop out. That's not so bad, right? And in Neo4j, it's not. And it's very fast because the way we store information is very much like linking list. So I'm just pointing to the next node and pointing to the next nodes. Computers are really good at following pointers. But in a relational database management system, going beyond 3 hops is really difficult. And we talk to a lot of customers, especially if their network is really large, where in order to go beyond 3 hops, it just takes too long and becomes impossible because if you think about it, you've got all of your information stored as tables in all these different locations, and you have to go to an index, look up, find what you're looking for, and then do a join, and then a join, and then another join, and then another join. And especially if we're talking 4 hops out, imagine how that fans out at each hop. You're fanning out to their friends as well. And so that can be very computationally expensive. It's very quick with graphs. And so that's an example of how you might use graph queries to do graph analytics offline. Another area that we see a lot of use right now is in graph algorithms. These are generally more unsupervised. And as I said previously, you're trying to understand the structure of your network. These are 5 different areas of classic graph algorithms. Pathfinding, how do I find the best route between A and F? What's the least cost routing for my phone call? Centrality, those are all about influence and importance. So who's the most influential person in the network? Or what's my biggest vulnerability? We see this a lot in cybersecurity and like utility bottlenecks. Where's my bottleneck would be an example of a centrality. Community detection, just what it sounds like. How do I partition my groups? Maybe I want to look at I just want to see the most tightly knit group or some groups that are kind of off on their own for some reason. So all about understanding the communities in your network. Link prediction is all about understanding and trying to predict relationships that will occur in the future. So are these 2 nodes likely to have an interaction in the future, or do they already have an interaction in reality and I'm missing it in my data? Similarity algorithms look at how alike nodes are based on attributes. So maybe it's based on their cuisine preferences, their zip code, whatever attributes you might include to an entity. It does it kind of a basic, almost like a set comparison. of what are the most similar nodes in my network. So I don't expect you to read this, but you can try if you want. We didn't even get all of them up here. So we have over 45 graph algorithms in Neo4j right now. We have a heavily used graph algorithm library, and the demand on that has been astounding for more algorithms all the time. We've got a lot of enterprise customers that are starting to use this, so we're actually developing another library. We haven't announced this yet, but we're going to extend the graph algorithm library and create a graph data science library, leveraging a lot of the similar algorithms, but we're going to add in a lot more enterprise capabilities like parallel graph loading. We have the ability, and we're adding in the ability to do seeding so that you can get more predictable results in production environments. Graph algorithms aren't all deterministic, so we had to add in some functionality there. We're going to start with a subset here and then continue to add on algorithms as well in that enterprise-grade library. That'll be available in the next few months, so you can either hunt me down on Twitter and bug me, or you can watch the Neo4j newsline and we'll let you know when that's available. So the next area that you can think about when you're walking along that path, so you've thought, we've got knowledge graphs. How do we help those domain experts? Graph analytics. How do I understand and gain insights from the data I already have in my network? And now with the graph feature engineering, you're using those same algorithms and queries, but now you're going to shoot them off into a feature vector, so metrics that are predictive, and use that in your machine learning models to increase your accuracy and improve your predictions. Now, feature engineering, if you're not familiar with it, it's just a fancy way to say I'm creating predictive components or predictive elements out of my data. That's it. You're engineering features. And you're usually combining information or doing some kind of an algorithm to create new information, if you will, or new data points that you can then do better predictions on. Now, when you do algorithms or queries to do this, you then have to shoot them out into a vector, and that's just a fancy way of saying a list of numbers. And here, ooh, you can't really see that, extraction down there, you then extract them into a list. Usually it looks like columns and rows of numbers, and then you run your machine learning on it. And the reason why people get really excited about graph and feature engineering is that, as I said earlier, data scientists always say, I need more information, I need more data. But if you already have fairly good accuracy, and you've reached kind of a plateau, and you just add more of the exact same type of information, you're probably not going to break through that plateau. What graphs do is they give you a different dimension of information, a different type of information. Those are those relationships that usually people aren't already bringing in. And so you can break through those plateaus by adding that different dimension. So a couple examples of using that. If we're using graph queries, this is the telecom-churn example. Telcos and telecom networks look very graphy. They translate to graphs very easily. But there was research to look at, can we just do with some simple queries, having the domain experts help us predict churn? Simple things like, how many calls did the person make in the recent past? What's their text patterns look like? Do they have any friends or people or their contacts that have churned recently? Once again, did mom churn? That should be an individual question there. But just those simple queries, they could output those into the numbers, into the vectors. And I don't expect you to necessarily be able to read this either, but at some point, right about here, they would basically have their experts say, which of these features that we've queried on appear to be predictive. We're going to spit those out into numbers, then do our machine learning on it, and they were able to get the accuracy to just under 90% using these really simple queries with the domain experts. So that's a nice, easy way. If you have a graph, if you have a knowledge graph already, you're doing machine learning already, for goodness sakes, these things are just pretty easy to test and get going with. Now, a little more advanced would be using the graph algorithms. And again, we're looking at structures here and trying to add in topology. I've included a fraud example here with a couple different algorithms that you could use. The first one is called connected components, or union find is another term for that. And that looks at groups of interactions that are usually grouped off on their own, I should say. So you might use this to look at people that are sharing some kind of identifier but aren't interacting with the big group. So in red here, the little circle, you can see these little floater groups, but they're not connected to the rest of the network. For some reason, that seems to be highly predictive of fraud and money laundering, is you have people doing things on their own, but they're not interacting with anybody else, or very few people. Another example is PageRank. Can I assume most people have heard of PageRank? Yeah, okay, cool. So PageRank is a really interesting history in that it was used to give credibility to web pages. Larry Page developed it. But it has been used in just about anything you can imagine, PageRank, because it's about influence. And it's about what has more influence in a network. So in this case, I don't expect you to see this little node out here. This little node had a lot of connections, but its connections had a lot of connections. So the way PageRank works is it infers credibility or ranking based on not just the number of connections, but the number of connections that your connections have. So it's very circular in that regards. And it can also be used to infer transaction volumes. So you can imagine lots of relationships. The relationship could be transactional. And you can look at that by different industries as well. So you might assume that certain types of banks or certain types of accounts have a high level of transaction, and that's normal, and other ones have a low level of transactions. So the way people deal with that is they do a personalized PageRank, personalized to a type of business, personalized to a type of industry, and then look at people with a high, or accounts or businesses with a high number of those transactions. Louvain modularity algorithm is another really interesting one in the fraud area. So Louvain tries to maximize tight connections within a community and lower connections between groups. So these two groups, as you can see, there's a lot going on there. There's a lot of connections there, but not so much with the bigger group. So they're not totally isolated, but the connections are lower. And so they would have a higher Louvain score in this case. And you can make estimations. You can also do hierarchies with Louvain, which is pretty interesting. The fourth one I've got listed here is Jacquard, and that's a similarity metric. So you might look at what accounts are most similar or have a lot of similar attributes. You may also try to develop a fraud profile. So perhaps your domain experts have said, hey, we know these 5 things about accounts normally indicate fraud, and I'm going to develop my own little fraud profile, and then I can just simply run similarity and say, hey, which, within 99% similar accounts to this one fraud profile, and then I can investigate those further. So the next area, and I actually will say before I talk about graph embeddings, the graph feature engineering is probably where we spend the most amount of time with our customers. A lot of low-hanging fruit, because customers that are already using machine learning can just bring in those relationships and see value right away. The next area that they're looking at usually is graph embeddings. And graph embedding is a type of feature engineering, so you're trying to do that predictive components or those predictive elements, but they're a little more complex in their structure. And so people usually talk about those in a separate context. People get a little more advanced when they get into that. Now, graph embeddings basically transform your graph into that feature vector, into those numbers that we believe, hopefully, may be predictive, or a set of vectors. And it describes the structure of your network, attributes of nodes, or the relationships of the graph itself. You can do feature engineering, the graph embeddings based on the node, just to describe all of the connectivity components of the node. I think one of the most interesting areas is the path embeddings. So this gets kind of exciting because you're not just embedding, what are these nodes like? What you're actually embedding is what is the path between all of my nodes? And imagine that looking at a path and how complicated that could be. It's impossible to do learning on that unless you can compress that into a numerical set, into that feature vector. You can also do it on the entire graph itself and create a complex vector on that. We don't see that used a lot except for in healthcare and chemistry. In those cases, there are reasons why that fits the biology a little better. Now, I'm not going to walk through how that works, but just to say, here's a visual for those of you that have looked at graph embeddings. This is a visual of the deep walk approach, where you're basically taking a random walk along your network. That gives you your traversal, your paths, and then you embed that, you do some training on that, and you embed that into your feature vector. I've just got 2 axes on here, an XY. You could have an XYZ. You could have many, many axes as well. So you can get very complicated with this. Now, all right, there's a lot there, a lot to unpack there, but why would you care about that? Well, actually, eBay gave us a really great example in a paper they put out about using graph embeddings for recommendations. And so this is a fun example in that there's a person they want to make a recommendation for. His name's Derek, and he happens to have listened to a song called Shape of You, and there's some kind of interaction with this song from Tony. I don't know what that is. Maybe he rated it, maybe he bought it. Anyhow, there's an interaction with Tony on that song, and Tony actually happened to interact with another song called I See Fire. Should I just recommend that to Derek? There's some similarity there, maybe. But there are many, many paths that you can take to get from Derek's listening of Shape to You to another song. Maybe it's who sung it. Maybe it's the album. Maybe it's a genre. And what graph embeddings allow us to do, in this case a path, is we're going to compress each one of those paths into a set of numbers. And then I can do machine learning on it and give you probabilities. And that's exactly what eBay did in this paper. And they can give you the probability, and I forget, it looks like Castle on the Hill wins. It looks like Castle on the Hill should be our recommendation, and it's through the genre that we should be recommending it. So hey, you like this song, here's another similar genre, here's another pop song that we think you may like. Now if they had recommended through the album, you might say, hey, we hear that you like the song, on this album is another song that you may like. So it allows us to tailor our recommendations. I think the idea of being able to learn based on a customer journey or their path, where are they on your website now? Where were they 2 seconds ago? I want to predict where they're going to be on the next click or the next hop. Are they going to go to Amazon to do a price check? What are they going to do? I think in recommendations, this is going to be huge in the future, because learning a customer journey and then being able to predict where they're going to go next with some probability is going to help serve customers better. The other area that I talked to, a lot of people are interested in the graph embedding and path learning is in patient care. So if you imagine taking care of a patient, especially if you have a long-term illness, there's a journey that patients take. And those fan out on every different diagnosis and every different test result. You could take a different journey. And so we've talked to a lot of people that are very interested in understanding patient journeys as well. And then, as you can imagine, being able to predict with a probability where it's most likely they'll get the best success taking a next step. So there we go. So the final area that we're really excited about in graphs and AI is the graph neural networks. And that's all about new ways of learning. And this is research that is going on now. I don't know of anybody that's doing it publicly or commercially right now. We're following this space really closely. Google put out the paper about a year ago. If you want the link, let me know. I'll get that to you. And basically, Google DeepMinds and several universities were looking at where are we going to go next with machine learning? We've made great advancements, but what are the shortcomings today, and how are we going to get over those? What's the next big innovation area? And what they came back to was that it was graphs. And they believe it's graphs because they can abstract about topology better than any other neural net can do. And they can actually do learning inside a graph. Now, what the heck does that mean? So it's a complicated paper. I won't pretend to understand all of it. But basically, the idea is you're doing machine learning inside of a graph data structure. And what's exciting about that is that you can input as a researcher with a graph format that you already have. And then as you do your machine learning, those transient states get maintained. It preserves those transient states. And then it outputs into a graph. So input, output looks alike, and I can preserve the transient state. Is anybody excited about this at the moment? Okay, we got a couple people that understand. Now I'm going to tell you the rest of you why this is so cool, because it is really cool. Is that what this allows you to do is track and validate your decision paths. If we've all heard about the terrible black boxes, uninterpretable results, not being able to explain things. So being able to track that path helps us understand and validate and trust the results a little bit better. So one, that's the first point we get really excited about. The other thing that we get really excited about, if you geek out on this stuff, is more accurate with less data. Now wait, I said that earlier, right? So we talk about adding relationships. But what's interesting in machine learning is you have to pick what to add. Your data scientist has to pick the features to add. So maybe color is predictive, maybe temperature is predictive, maybe credit score is predictive. You don't know ahead of time, but you have to do your machine learning. That's part of what you pay your data scientist to test all these different models. We believe with a graph native learning that the graph native learning can help tell us and inform us what features are really predictive. And that'll help us get to models faster, and will also help us potentially from overfitting as well. So we get pretty excited about that. It is kind of a little future looking, but you can see where there's very practical steps that you can take to go from what seems fairly simplistic today with a knowledge graph to some very advanced things in the future. Knowledge graphs, if you're not using them now, they are the framework and the foundation for graph data science. It's a great place to start because you can get value right away by giving your experts more tools to make better predictions, and then you can easily layer on other functionality as you get more advanced. We have several resources for you guys in the audience. For people who just want to look at kind of the general context, maybe the business level, we have a white paper online. If you're a data scientist, take a look at our sandbox. We have an algorithm sandbox. You don't have to load anything. It's all hosted online. We've got the algorithm sandbox has data from Game of Thrones, so it's a lot of fun, and it has tutorials as well. Developers in the audience, I highly recommend our desktop. So you can download our desktop. It acts like a portal into Neo4j. And the Graph Algorithms book that you have posters out there, it's free online at Neo4j for at least another 4 or 5 months. So early next year it won't be, so get it while it's available. I brought a copy, so if you guys just want to thumb through it and see if you really want the electronic version, but you really want the electronic version. So we've talked about a lot of things today, and I'm happy to meet with anybody and we can talk more about ideas, but there's really just, you guys can forget everything else that I've said, maybe, no, you can forget everything else. I just want you to remember one thing from here, and that AI does not just equal machine learning. You can't just do machine learning and expect great results. You have to add in context and structure to have more accurate and more informed machine learning and artificial intelligence. So with that, I appreciate everyone's attention and patience through the microphone issues. Come find me. I'm easy to find on Twitter. I've got an unusual last name, so I'm pretty much easy to find on the internet. So appreciate, and I'll talk to some of you later.